Okay, this is a big subject change. We're looking at a new concept here. We're not looking at math. We're looking at something that's more like science. In biology, they classify the animals. You have fish, you have reptiles, you have mammals. In math, we classify our numbers. And we have different group names for the different numbers. And the first group name, that's the set of numbers that I want you to learn about, is the real numbers. Think about everything in this box is all the real numbers. Now, in the box of real numbers, they're going to break down into other groups, like our animal kingdom. You break down the animals into mammals and fish. So mammals have one pattern and fish have a different pattern. Real numbers break down into two big patterns. One pattern is the numbers that are called rational. I'm going to use this little pound sign or hashtag sign as an abbreviation for the word numbers, versus another group that is called irrational. Oops, I need to irrational. Sorry, my spelling can be really bad sometimes. Okay, now what's the difference between these two groups? These are fractions. Rational numbers are just fractions. Irrational numbers, ir just means not. So this group, they're not fractions. There's a bunch of numbers out there that we cannot make them into fractions, and a bunch of numbers out there that we can make into fractions. Now I want to concentrate on this rational group, because if we break down the real numbers, like all animals, into mammals, the mammals break down into other groups, like dogs. And the dogs break down into other groups, like hunting dogs and pets. And those break down into like poodles and chihuahua, so we can keep breaking down this animal kingdom. But the rational numbers are fractions, like -7 over 3 or 8 over 5. But this group of rational numbers breaks down into a simpler fraction, and let's make a box inside the box called integers. Because integers are a special kind of fraction, like 6 over 1, or -7 over 1, or even 0 over 1. These are all integers because 6 over 1 is 6, -7 over 1 is 7, -7, 0 over 1 is 0. These are special kind of numbers that we call the positive, the negative, and 0 counting numbers. All right, now in that group, we can break that group down smaller into a smaller group. Now these last two smaller groups are not super important, but the categories do exist. These are the whole numbers. Now, what are the whole numbers? They are zeros and the positives. So that would be like 0, 1, 2, 3, ... That's the whole numbers. Now inside the whole numbers is a final group that we're going to call the natural numbers. Now what are the natural numbers? The natural numbers are 1, 2, 3, ... So we count with the natural numbers. That's nature. Now if we take the natural numbers and combine it with 0, it makes the whole numbers. If we take the natural numbers and combine it with 0 and combine it with the negatives, it makes all the integers. Now if we take all the integers and combine it with all the other kind of crazy fractions, we get all the rational numbers. And then lastly, there's this other group, the irrational numbers. The irrational numbers are a little bit more unusual. They're numbers like pi, like the square root of 2. the negative square root of 17. When you go into Algebra 2, there's a special number called e that's very similar to pi. Now, here's a note about these irrational numbers. They're decimals. Because I'm going to give you a number, and I want you to tell me, is it rational or irrational? And if it's a decimal, here's how you know. The decimals never stop, never repeat. If it's a rational number, the decimal will always stop or repeat. So like 12, the decimal stopped at, there's no tenths or hundreds. 25, the decimal stopped. So you get 25. 1.3, the decimal stopped after 3/10. These are rational numbers, and we know because they're decimals are stopping. There's other numbers where the decimal repeats, like 1 divided by 27. It's a fraction. And if you look at that, you get 0.37, 0.37, 0.37. There's a rational number, and its decimal is repeating on us. If you get any decimal that repeats, you know it's. There's a glitch there, but let me restate where we finished off before the glitch. If you get any decimal that is repeating, like this one, 0.37, 0.37, you know how to classify it. It is a decimal that repeats. Therefore, this number has to be a rational number. Now, we see the fraction of it, 1 over 27, but sometimes all you see is the decimal. Like down here on number 6, you don't see the fraction. Is that a rational number or irrational number? And that's how we do the repeating sign there. It's 4.5666666 repeating. So it repeats, so we know that's going to be one of these rational numbers. So that's how you classify it. But what about the irrational numbers? Their decimals never stop, never repeat. For example, the square root of 2. Let's take a look at the square root of 2. Okay, I pulled this math website up. It's called Wolfram Alpha. It's a powerful math website. And I typed in the square root of 2. Had to type it in a fancy way here for the computer. And I said, do the square root of 2 to 100 digits. And if you look at it, you might remember we did this. 1.414213. We only had like 7 or 8 digits here. And Wolfram went all the way out to 100 digits. And if you look at this pattern, it has no repeating. Now, it stopped at 100 because I told it to stop at 100, but actually the square root will never stop. If we tell it to go further and do 500 digits, it'll keep the calculation of all the decimals all the way out to 500 digits. And if you study that, you will never see a repeating pattern. You might see like 99970. Is that repeating? Well, no, because there's no more 9999s. It's just brand new after that. There's no repeating patterns. This can go out to 2,000 digits. Oh, I put in 20,000. Let's see what it does. Ah, there it is. Oh my goodness. That's square root of 2. Calculated out to 20,000 digits. And there is no repeating in here. You study that, you will never find a repeat pattern. Man, I haven't got to the bottom yet. This is amazing that the computer can do that. But my point is, anytime you see a crazy decimal like that with no pattern in the calculator, it's likely an irrational number. So that's how we know the difference. Irrational numbers like the square root of 2, the decimal will never stop, never repeat. Okay, now there's another way to classify, not another way to classify them, but another way to draw this with a branching diagram, but I'm not going to do the branching diagram because we've already made this lesson I've already made it kind of long. But I want you to be able to categorize these numbers. And so what does that look like? Let's classify each number in the problems below. So you need to put a check mark by each number set. Negative square root of 17. What kind of number is it? Is it a natural number? Is it a whole number? Is it an integer? Is it a rational number? Is it irrational? Now, if it's a natural number, it's like a poodle. A poodle is a dog, and a dog is a mammal. Well, no, it's like a poodle, which is in a category of dogs, which is in a category of pets, which are mammals. So what natural numbers are, if anything's a natural number, it's also a whole number, it's also an integer, it's also a rational number. But natural numbers or irrational numbers are classed by themselves. So look at the square root of 17. If you're not sure, try the decimal. Clear square root 17. Are we getting a nice decimal? Is there a repeating? Does the decimal seem to stop? Well, it ran the whole calculator out of room and there's no repeating. That's a strong suggestion that we're dealing with irrational. So it's not a natural number because natural numbers are just counting 1, 2, 3s. Same with whole numbers, same with integers. This is this crazy decimal. So it's none of these, but it is irrational. Now, irrational numbers are inside the group of real numbers. So it's also a real number. What about negative 2? Is negative 2 a natural number? Nope. It's not a natural number because natural numbers are all positive counting numbers. Is negative 2 a whole number? No, because whole numbers start at 0. So it's not. Is negative 2 an integer? Yes, integers are positive and negative counting numbers. So I'm going to put a check mark. You don't have to put the x's in there. I'm just putting the x's for emphasis. Is negative 2 a rational number? That means, does its decimal stop or repeat? Yes, it stops at 2.0. It's also a rational number, which means we can make it into a fraction. Is that a fraction? Well, negative 2 over 1 is a fraction. Yes, this is a rational number. If it's rational, then it's not irrational. I'm going to make my x's smaller so they don't look like I'm including them. Is negative 2 a real number? Well, all the numbers we know are real numbers. If it's a rational number, it's in the real number set. So we can put a check for that. So this is how this goes. Negative 9/37. Is that natural? Nope, we don't count. We only count in things with nature like 1 sheep, 5 sheep, 10 sheep, 8 potatoes, 11 potatoes. We don't really count with fractions in nature too much. So no. Is it a whole number? No, those are 0 and 1, 2, 3 counting numbers. Is it an integer? Nope. Integers are positive and negative counting numbers. Is it a fraction? Sure enough. So 9/37 is a fraction. That makes it a rational number. Is it irrational? Well, if it's rational, it's on this side. It's not on that side. So it's not irrational. It's going to have a decimal. But it's a fraction. We can see it's a fraction, so we know for sure it's rational. And all numbers are real numbers. Check. What is 0? What types of number is it? Is it in the natural number set? No. Is it in the whole number set? Yes. Whole numbers have 0. Is it an integer? Yes. Integers can be a fraction, 0 over 1. It's also a fraction, 0 over 1, so that makes it a rational number. But it's not irrational because the decimal stops at 0.0. But it is a real number. Okay. Now, negative 6.06. Notice the decimal. It doesn't keep going. 0.06, end. It doesn't keep going. The decimal stops. If the decimal stops, does that make it irrational? Nope. Irrational numbers, their decimals never stop. So it's not irrational. If it's rational, the decimal will stop, and this one stopped, so we have a rational number here. Now, is it an integer? Nope. Integers, -6 would be an integer, but not this decimal number. So it's not an integer, and if it's not an integer, it's not whole, and it's not natural. Is it a real number? Yes. Basically, short answer, all our numbers are real numbers. That's a check mark. Check. Okay, 4.5, what does that bar mean? It means 4.56666, dot, 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 dot. 6 is going forever. It's repeating, and we learned, oh wait, repeating, is that irrational? Irrationals never repeat. This one is repeating. Oh, that makes it a rational number. So we can go check. If it's rational, it's not irrational, so we're not going to include that. And all numbers are real numbers, so we can put a check there. Now, is it a natural number that we can count with? No. Whole number? No. Is it integer? No, because these are all integers, whole numbers, and natural numbers are counting numbers, sometimes with 0 and positives and negatives, but this is not. Okay, last one I'm going to do. This is tricky. It's got a decimal. Since it's a decimal, it's not a whole number. It's not a natural number, not a whole number, not an integer. And all numbers are real numbers. So we got that. Check. Is it rational or irrational? Okay, now we can look at the decimal and figure out if it's a decimal that repeats, it will be rational. If it's a decimal that never repeats, it's irrational. Now it does have the dot, dot, dot. So it's not stopping. So it's not about stopping, but could it be repeating? Is there a pattern? Well, it goes 0, 5. Now does the 0, 5 repeat? Well, the next three are 0, 0, 5. Does that repeat? Well, the first one only had 1 0, and this one has 2 zeros. Okay, does 2 zeros repeat? Well, the next one is 0, 0, 0, 5. That one has 3 zeros. So first there was 1 0 and a 5, then there's 2 zeros and a 5, then there's 3 zeros and a 5, and then there's a pattern. The next part in the pattern would be 1, 2, 3, 4 zeros and a 5. Is this repeating? No, it is not repeating. The pattern keeps changing because it keeps adding in an extra 0. So we don't have like a 6666, or we don't have like a repeating of the same thing. 1 divided by 27, 037, 037. So this guy is a very creative invention, but it is not repeating. This is repeating 037, 037, 037. But this one keeps putting in more zeros each time and makes it longer and longer. So this sequence is not the same as the first sequence. It's not repeating. This is never stopping and never repeating. This is an irrational number. That's kind of an unusual one. That's why I wanted to talk about it with you. But it's irrational. Okay. Wait, one more. What's negative 43 over 0? In case you forgot, negative 43 divided by 0. Can we divide by 0? Error. No. This does not exist. It is not a number. So, this is not a real number. It's not a real number. It's not any of these. It's nothing. It's none of these things. So they all stay blank. There's 2 left. I want you to do the last 2. And so we'll quit there. Study hard on this. This was a long lesson. Sorry about that. I think it was important, though, to get it done, and it'll help us when we start off on chapter 2 on Wednesday. Hang in there. Keep working hard. You guys are doing great, and I'll see you on Wednesday.